Hello, everyone. My name is Zhang. I'm a fifth-year PhD student working with Chris Harrison at Carnegie Mellon University. Today, I'm really excited to be here to present our work on Sozu, which is self-powered radio tags for building-scale activity sensing. As we all know, that Internet of Things and smart environments rely on robust sensing approaches that can detect a wide range of user activities, from opening and closing of a door to operating machines such as stove, microwave, lights, and etc. However, the most common approach relies on battery-powered tags, which requires user maintenance, right? It might be fine for one or two of such battery-powered sensors in the environment, but imagine a room with dozens of these sensors, or a building with hundreds, if not thousands of these sensors. Replacing the batteries at the end of the day simply become very impractical. In response, people have explored battery-free sensing approaches. For example, we can have sensors that can be plugged in for power. We can also have a battery wireless transfer technique that transfer power wirelessly, for example, the UIST project, or we can use backscatter technologies such as RFIDs. However, these approaches usually cost more than $10 each, which collectively add up the cost for building-scale sensing instrumentation. Also, they have low sensing versatility. For example, I can only sense electrical appliances, or I can only sense things that move. Or they have limited sensing range. For example, RFID or backscatter technologies, they in general do not do well if the distance between the reader and the sensor is beyond 15 meters. To overcome these limitations of the previous work, we set several design goals at the beginning of these projects. Right? First, we want our sensor to be low cost. Ideally, each sensing unit should cost less than $10. Also, we want our sensing technique to be long range, which means the signal from each activity source should be able to travel long distance without line of sight and can be detected remotely. We also want our sensor to be battery-free, which significantly lowered the user maintenance cost. And finally, we want our sensor to be rich sensing, meaning that we can not only sense electrical appliances, but also things that are passive, also things that move around or generate other types of signals, such as light, thermal, or vibration. In this project, we achieved about 4 design goals with Sozu tags, which convert the energy from the very activity they want to sense into radio frequency broadcast. Here is one of the examples where Sozu tag is on a blender, which provides vibration energy. When the blender is being used, the Sozu tag converts the vibration energy with some help from piezoelectric material into radio frequency broadcast. Such frequency broadcasts then travel through walls and floors and can be detected by a centralized antenna that we envision to be in future integrated into a Google Home or Alexa. Beyond vibration, we also found that human activity also induces many other energy types, for example, thermal, light, and motion. So we did a survey on a wide range of activities and found 7 common energy types, from motion to water flow. So we use off-the-shelf energy harvester to convert this energy into electricity. I will just go through this energy harvester very quickly. So motion from activities such as opening a pill bottle or pruning the garden can be converted with coils, with magnets. Some power tools and appliances also generate vibration energy, which we harvest using piezoelectric materials. Solar and light is another common source which can be used to infer, for example, opening of a refrigerator door or room occupancy. We harvest these type of energy using solar panel. Many appliances generate thermal energy, for example, the stove, hot glue gun, fireplace, or gas engines. To harvest this energy, we use Peltier junctions. There are also electrical appliances which generate electromagnetic radiation. To harvest the energy from those appliances, we use coils with ceramic cores. And finally, there are flows from gas and flows from water. And to harvest this energy, we use brushless DC motors in connection with the corresponding fans. So we know we can harvest energy, but how much exactly in practice? So we did a study with 50 different activities. We found an average energy power of 2.7 milliwatt. But as you can see here, there is a long tail effect, which means for some activities that generate very low power output, it requires the tag that we later design to be able to first store the energy until it builds up enough to then use this energy and for transmission so that it's more efficient. Once we understand our energy budget, we also investigated, okay, what frequency range our tag should be operating at. So we did a data collection from 6 different locations and found the energy, the frequency and noise profile like this. Eventually, we selected the frequency range from 35 megahertz to 85 megahertz. As you can see, this allows us to steer clear from the environmental noise and also allow us to comply to FCC regulations. And more importantly, with this frequency, signals are very good at penetrating common building materials, as is shown here, which we also verified with a small benchmark study. So with all knowledge we gathered from the previous investigation, we built our Sozu tag. Just want to remind you guys, we want our Sozu tag to be cost less than $1, right? This eliminates any use of digital components such as Bluetooth or Wi-Fi. So instead, we design everything with analog components. Here are the final designs. So our Sozu tag features a rectification stage, which means we can harvest both DC and AC electricity. It also has an energy storage and management stage. Specifically, by using this thyristor, we can monitor the voltage on the energy storage capacitor. Once it goes beyond certain threshold, the thyristor shorts itself. This allows the energy stored to be dumped all at once to the next stage, which is this RF oscillation circuit. Here, I want to mention one part, which is the Miller capacitance between the collector and the base of the transistor. This basically allows us to do a simple frequency modulation, which means we can use the received frequency to reconstruct the voltage provided by the energy harvester. This allows us to do both detecting the presence of the activity, but also infer the states and the direction and the rate of an activity. So for people who are not EE engineers, this is basically a miniaturized radio station, which converts the energy from activities to radio frequency broadcast. So here are some high-level specs of the Sozu tag. As I mentioned, we are doing frequency modulation. Each tag has this bandwidth of 0.5 megahertz. For continuous broadcasting, the Sozu tag consumes power of 2.05 milliwatts. And for the minimum energy it requires to generate one frequency broadcast is 0.12 millijoule. And we achieve the goal of having our sensor tag less than $1 for bulk production. So once the Sozu tag emits signal, we also need a way to collect the signal from the environment. So here, as you can see, there are 3 components of the Sozu receiver: an omnidirectional wideband antenna, a software-defined radio, and a laptop for computation. So because our signal can penetrate through building structures, we can hide this receiver out of user sight, in this case, in a user's basement. Since our Sozu tag converts the energy from activity that we try to sense, right? Detecting the activity simply becomes detecting the presence of the corresponding RF signal in the environment. So we first randomly assign activities to different frequencies so they don't overlap. Within each activity's bandwidth, which is 0.5 megahertz, we look for the Sozu tag signal by calculating the max to mean difference and then threshold on that signal for activity detection. We use this technique to make our sensing pipeline more robust to environmental noise, which is more like a wideband signal, and also it compensates for the antenna sensitivity difference across different frequencies. We also use exponential moving average and a majority volter to make our pipeline more robust to transient noise. Here you can see a short video of our Sozu tag in action. So let me walk through what is going on here. So on the bottom right, we have the receiver deployed in that basement. The rest 3 things are from cameras deployed outside that building in the garden. So now someone starts chopping. As you can see, each chop can generate enough energy for the broadcast. And then garden hose being used, and finally someone turned on the mailbox. This was fast. I will play the video again. So first, someone starts chopping, and garden hose being used. As you can see, the frequency shows up at different frequency, and then finally turning the flag. So we also evaluated Sozu at 3 different locations in the course of multiple weeks. And I will just go through this result very quickly. Please refer to the paper for more details. So the result was very encouraging with a true positive rate higher than 99% and extremely low false positive rate. So beyond just detecting the presence of activities, I also want to demonstrate some rich sensing opportunities which we achieved. For example, we can strategically place the magnets on a door, a sliding door, so that we can detect the direction of the door. For example, being closed, being open. So this basically allows us to tell whether the door is being closed or open, rather than simply saying someone moved the door. We can also detect user grasp or engagement by incorporating user's body into the RC oscillation circuit. Here, as you can see, we attach the cover to where user have to grasp, so that when the user's body is in contact with our sensor, right, it shifts the frequency a little. But based on that, we can detect whether the user is currently engaging with the hot glue gun. So we can not only detect whether the hot glue gun is on or off, but whether it's on, but nobody has been using it. So we can then send an alert message to facility people to give a check. We can also leverage the frequency modulation to build some simple analog sensors. Here, as we can see, is a light intensity sensor. And similarly, we can also detect the water flow rate for a fine-grained water usage sensing. Also, if we have multiple receivers in the environment, we can also triangulate the location of an activity. We did a study. Here, as you can see, there are 4 antennas deployed at the second floor of a 2-floor building. And then we perform activity with Sozu at both floors and also outside the building. And here are the results. So as we can see, the result at each tested location. So on average, we achieved the tracking resolution of 4.1 meter. So this coarse activity tracking allows, for example, multiple objects at different locations to share the same frequency. For example, we can assign all the faucets in the building at the same frequency because they cannot physically overlap, right? We can still use the location as extra 1 bit of information to disambiguate which is which. This also allows our Sozu system to be robust to, for example, neighbor's Sozu system. That we can use this location information to ignore signal from other Sozu systems. To help others get quickly hands-on experience with Sozu, so we open source this technology. With this URL, you can find all the source design files. We also created a Sozu toolkit, which I've been giving away at UIST, specifically at the demo section. So please also come to me at the end of the section if you want to have a Sozu toolkit. So we were really excited to see what others might create with our sensor. So we loaned the device to 8 students at CMU, and they came back to us with their individual projects, with their idea after 1 week. I will just conclude my talk with some of the student projects. So first is a smart parking sensor. So the student made this sensor with a solar-powered Sozu tag. And he also made this waterproof and dustproof by curing everything inside of an epoxy resin and 3D printed shell. So the student placed the tag on the ground on a parking spot. When the car parked above it, it attenuates the light energy, which we can monitor by sensing the shift of the frequency. Right? With this sensor, we can know whether the spot is taken. Then we can post the information online for visitors so they don't have to travel all around this campus just to find a parking space. There's also a smart recycling bin. The student cut a hole toward the top of the recycling bin, and using a solar-powered Sozu tag, whenever the recycling bin is full, it's covered by trash, and we can then send an alert message to facility people instead of them having to check manually every day. Another student created a smart accessible door for wheelchair. So she put a motion power Sozu tag to the wheelchair and then put the antenna at the door. She attenuated the antenna sensitivity so that the antenna only senses the Sozu tag when the wheelchair is within 2 meters range with that door. And finally, there's a smart medication reminder. So the student instrument the lid of the pill bottle, so they can every motion of opening and closing the lid can generate a unique frequency broadcast. Then the Google Home or Alexa can detect when to remind the patient to take medicine. Okay, that's my talk. Thank you very much. I'm open to questions.
So we have time for several questions.
Thanks for a very great talk. I'm just wondering, given that you're not using Bluetooth or Wi-Fi technology, what are your thoughts on privacy and security, given that even though you may have ways to not be, to listening into your own signals, you still can listen into everybody else's signals as well?
Yep, that's a great question. Actually, security and privacy is definitely one of the loopholes of this technology, because we are not encoding information, which means your neighbor or someone with bad intention can just park long enough outside your house and monitor what is going on inside the house. So one thing I would say is because the table, right, to link frequency to the specific activity is maintained by the homeowner. So even though someone outside your house detect some signal, but they don't have that table, they don't know what exactly the user is doing inside the house. But I agree with you. So with this technology, you still can sense someone is inside the house or not. That's a limitation of the technology. I bet in future, if we want to improve this technology in future, we can add some, for example, like delay on the analog circuit. So instead of like real-time broadcasting signal in real time, we can broadcast signal, for example, with hours of delay, or add some random noise so that you can decode the random noise. You know the random noise from the receiver, but other people don't know the random the encoding. So that might be some way to solve the privacy problem.
Hey,
Yeah.
Thanks for the great talk. I have a question about in your kind of system evaluation, you showed very impressive accuracy numbers, and I myself have used some precursor technology like the piezoelectric light switches that you can install that harvest energy from you pushing the button to control an outlet somewhere, and the reliability of those is very poor. And so I'm wondering if you can comment on, and they're out there as commercial products and very, very much below deterministic in their operation. If you can comment on some of the challenges that those products are facing that you might also be facing or that you've overcome with a different approach.
Yes, that's a great question. So we noticed that some of because we literally have to connect the Sozu tag with the harvester, right? There are wires there, right? If you don't protect them well, right, with the exposure of element outdoor, it can easily be damaged. So one example of how to protect that, as I showed in one of the student product, is to pour silver epoxy so that eventually everything is just one part. There's no moving part there. Everything is so dust and waterproof. And we're also counting on, for example, collaboration with manufacturer of everyday goods to incorporate our technology to part of their manufacture process. Because our technology is super low cost. It's low cost enough that it gives the unique opportunity for future, manufacturer of this passive object to incorporate the technology during the manufacture process, so we don't have to add anything external. That could be another way to make it more robust. Because right now, because this is like first time we try to build this technology, a little bit like researchy and prototyping. But I agree with you. The durability could be one of the limitations.
We've got time for one more quick question.
Hi, great talk. I just have a short question. You talk about signal penetration. Then what material cannot be penetrated? What would be the limitation of deployment?
So let me repeat your question just to make sure I get it right. So if there's one material that we cannot penetrate through, what would be that material?
Yeah.
That would be a big sheet of metal. But yeah, with this frequency, we found that the wavelength, right, is very good at penetrating the modem material. But still, we notice some, for example, attenuation if your receiver is next to a big sheet of metal, such as a refrigerator, right? Because the door is literally like a big thick of metal. So that could be attenuation if the receiver is next to that.
Thank you very much.
Let's thank our speaker one more time.